What if I told you that everything around you, the stars, the planets, even the device you're watching this on, might have sprung into existence from absolute nothingness? It sounds like science fiction, but this is the jaw-dropping question physicists and philosophers have been wrestling with for decades. Picture a moment before time, before space, before even the tiniest particle flickered into being. A pure, unfathomable void. How could our universe, with all its complexity and grandeur, emerge from such emptiness? This isn't just a thought experiment, it's a frontier of modern cosmology, and the answers might rewrite everything we thought we knew about reality. The mystery of cosmic origins grips us because it's not just about distant galaxies or abstract physics, it's about us. Every atom in your body, every ray of sunlight, every whisper of wind traces back to that primordial moment of creation. Scientists call it the ultimate question, and tackling it means venturing into realms where the laws of physics as we know them break down. Some theories suggest our universe bubbled up from a quantum fluctuation, a tiny ripple in the fabric of nothingness. Others propose we're just one bubble in an infinite multiverse, a cosmic froth of universes popping in and out of existence. And then there's the haunting possibility that nothing might not be what we think it is at all. So buckle up, we're about to embark on a journey that stretches the limits of imagination. We'll dive into the wildest ideas cosmologists have dreamed up, from the mathematics of nothingness to the mind-bending concept that the universe might have created itself. Along the way, you'll meet the brilliant minds daring to confront this puzzle, and you might just walk away seeing existence in a whole new light. Because if one thing's certain, it's this: the story of how everything came from nothing isn't just science, it's the most epic origin story ever told. But what exactly is nothing? It seems like the simplest idea, just empty space, right? Yet when you peel back the layers, nothingness becomes one of the most slippery concepts in science and philosophy. Close your eyes and try to picture true nothingness. No light, no sound, not even the faintest hum of energy. No up or down, no before or after. Most of us can't truly grasp it because even our language fails us. We describe nothing by what it isn't. Ancient Greek philosopher Parmenides threw up his hands and declared that nothingness couldn't exist at all, because speaking about it somehow makes it a thing. Fast forward 2,000 years and quantum physics flips the script entirely. What we once called empty space is actually a seething quantum foam, where particles wink in and out of existence so fast we can barely detect them. This isn't just academic wordplay, it's the foundation of the cosmic mystery. If we're claiming the universe came from nothing, we'd better define our terms. Is nothing a blank slate, or is it pregnant with potential, like a seed waiting to sprout? Some theories suggest that what we call nothing might be a hidden realm of mathematical laws or quantum fields, invisible scaffolding that makes existence possible. Others argue that even time might not be fundamental, that it emerged after the universe began, meaning there was no before to speak of. The more we learn, the clearer it becomes. Our everyday idea of nothingness is like a child's crayon drawing next to the vast, intricate canvas of reality. So when we ask whether the universe came from nothing, we're really asking two questions. First, what kind of nothing are we talking about, a sterile void or a bubbling quantum cauldron? And second, could any form of nothingness truly explain the breathtaking complexity around us? The answers might lie in the strange marriage of philosophy and cutting-edge physics, where the most profound mysteries of existence are slowly coming into focus. Long before the first equations of quantum physics or the discovery of cosmic microwave background radiation, humanity was already spinning tales to explain the birth of everything. Take the Babylonian Enuma Elish, where the universe emerges from a swirling chaos of saltwater and freshwater gods Tiamat and Apsu, locked in primal conflict until order is carved from their divine remains. Halfway across the world, the Rigveda's Nasadiya Sukta wonders if even the gods know how existence began, describing a time before time where there was neither non-existence nor existence. What's striking isn't just their poetic beauty, but how these ancient stories grapple with the same paradox that keeps cosmologists up at night. How can structure arise from formlessness? Why is there something rather than nothing? These myths aren't just quaint curiosities, they're early drafts of humanity's operating manual for reality. The Hindu concept of an endlessly breathing cosmos, where universes expand and collapse like waves, uncannily echoes modern theories of cyclic cosmology. The Maori story of Rangi and Poppa, Sky Father and Earth Mother wrenched apart to create space, mirrors the inflationary expansion scientists propose happened fractions of a second after the Big Bang. Even the biblical "Let there be light" finds a scientific cousin in the sudden flash of recombination when the universe became transparent. What these traditions share is a recognition that creation isn't just an event, it's a transformation of the very rules of existence. Yet there's a crucial difference between ancient wisdom and modern science. Where myths often relied on divine hands or cosmic eggs as ultimate explanations, today's physicists demand mechanisms. Nobody gets to say, "a god did it," and call it a theory, but the parallels remain profound. Both traditions confront the limits of language when describing pre-creation states, whether it's the Aboriginal dreamtimes, everyone, or quantum physicists' false vacuum. Both wrestle with causality's breakdown at the moment of origin. How can there be a cause without time? Most tellingly, both reveal our species' refusal to accept mystery without a fight. From shamans studying the stars to astronomers studying redshift, we've always been driven by the same awe-filled question: what set this whole magnificent show in motion? Perhaps what these stories teach us isn't about the universe's birth, but about our own minds. The fact that cultures separated by continents and millennia arrived at similar metaphors, cosmic trees, world turtles, vibrating strings, suggests something fundamental about how humans process the incomprehensible. We build bridges of narrative across the abyss of the unknown. Today's equations about quantum fluctuations may be light years removed from the Norse giant Ymir's flesh becoming the Earth, but they're still stories just tested against mathematics rather than campfire retellings. And that continuity is what makes our modern search for cosmic origins feel not just scientifically vital, but deeply human. After all, every time a physicist peers back toward t=0, they're standing on the shoulders of the very first storytellers who dared to ask where the night sky came from. For centuries, Isaac Newton's vision of the cosmos held sway, a vast, unchanging stage where stars and planets moved like clockwork through infinite space and time. To Newton, the universe was a perfect, eternal machine, crafted by divine hands and needing no explanation for its origins. It was a comforting idea, stable, predictable, and seemingly complete. But science has a way of upending even the most deeply held beliefs. In the early 20th century, astronomer Edwin Hubble peered through his telescope at Mount Wilson and noticed something astonishing: galaxies weren't just drifting in place, they were racing away from each other at incredible speeds. The universe wasn't static at all. It was expanding, stretching the fabric of space itself. This revelation shattered Newton's eternal universe. If everything was moving apart, then rewinding the cosmic tape would mean all matter and energy were once compressed into an unimaginably dense point. The implications were staggering. The universe had a beginning, a moment when time and space burst into existence. Hubble's discovery didn't just overturn Newton's model, it forced scientists to confront a question that had been lurking in the shadows for millennia. If the cosmos wasn't always here, then how did it come to be? The answer would eventually take shape as the Big Bang Theory, but the road there was anything but smooth. Newton's framework, brilliant as it was, had a blind spot. It couldn't account for change on the grandest scale. His laws explained the motion of planets and the fall of apples, but they assumed an unchanging backdrop, a universe without history. Hubble's expanding cosmos revealed a dynamic, evolving reality, one that demanded a new kind of origin story. And so, the search for cosmic beginnings shifted from philosophy and theology into the realm of hard science. The question was no longer whether the universe had a starting point, but what that moment looked like and what forces could have sparked it into being. What's fascinating is how close Newton came to glimpsing the truth. His own laws of gravity hinted that a static universe might be unstable, a fact that troubled him. To explain why the stars didn't simply collapse inward, he suggested God must occasionally intervene to keep everything in balance. Centuries later, Einstein faced a similar dilemma with his theory of general relativity. When his equations predicted an expanding or contracting universe, he added a cosmological constant to force a static solution, a move he later called his greatest blunder. Both geniuses stumbled over the same idea: the universe might not be eternal after all. It took Hubble's bold observations to finally pull back the curtain, revealing a cosmos with a dramatic origin story, one we're still piecing together today. This shift from Newton's timeless universe to Hubble's explosive beginning didn't just change astronomy. It transformed how we see our place in the grand scheme of things. No longer were we living in an unchanging, infinite void. We were part of an unfolding epic, a story that began with a single, unimaginable moment, and that realization, that the universe had a birthday, set the stage for the next great leap in our understanding, the hunt for clues about what sparked everything into existence. Imagine the scientific uproar in 1927 when a Belgian priest named Georges Lemaitre stood before his colleagues and suggested something radical: that the universe wasn't eternal, but had exploded into being from an unimaginably dense point he called the primeval atom. At the time, even Einstein resisted the idea, dismissing it as suspiciously close to biblical creation. But Lemaitre, both a physicist and a man of faith, wasn't proposing theology. He'd arrived at this conclusion through mathematics. His equations showed the universe expanding, which meant if you ran time backward, everything would contract until all matter and energy were crushed into a single, scorching point. This explosive beginning would later be mockingly nicknamed the Big Bang by critics, a label that stuck despite its playful origins. What made Lemaitre's theory revolutionary wasn't just the idea of a cosmic beginning, but the evidence that eventually backed it up. Decades later, two radio astronomers named Arno Penzias and Robert Wilson stumbled onto something extraordinary: a faint, persistent hiss coming from every direction in space. At first, they blamed pigeon droppings on their antenna, but after scrubbing the equipment clean, the noise remained. This turned out to be the echo of the Big Bang itself, cosmic microwave background radiation, the cooled remnant of that initial fireball, still whispering across the universe 13.8 billion years later. It was the smoking gun that transformed Lemaitre's hypothesis from fringe idea to cornerstone of modern cosmology. Yet for all its explanatory power, the Big Bang theory doesn't actually answer the ultimate question. It just pushes it one step further. If the universe began as a superheated speck, what existed before that? Was there a before at all? Lemaitre himself avoided speculating, calling the moment of creation a day without yesterday. But this is where things get truly mind-bending. The laws of physics as we know them break down at the instant of the Big Bang. Time and space as we understand them didn't exist yet, so asking what came before might be like asking what's north of the North Pole. Some physicists propose that the Big Bang wasn't the absolute beginning, but a transition from some other state, a bounce from a previous collapsing universe, or a quantum fluctuation in a deeper vacuum of reality. Others suggest time itself emerged at that moment, making the question meaningless. What's clear is that the closer we get to t equals 0, the stranger the cosmos becomes. The Big Bang theory didn't just give us a new origin story, it revealed how much we still don't understand about the nature of nothingness, and whether that word even applies to whatever, if anything, preceded everything. This is why the Big Bang remains one of science's greatest triumphs, and its most humbling frontier. It explains so much about how the universe evolved, yet leaves its deepest mystery untouched. We can trace cosmic history back to a trillionth of a second after the explosion, but at the moment of creation itself, our equations dissolve into chaos. Perhaps this is the ultimate lesson, that the birth of the universe might always hover at the edge of comprehension, a reminder that some mysteries aren't puzzles to be solved, but horizons to be endlessly explored. Here's where quantum physics throws our intuition out the window. That empty space between stars and galaxies, it's actually a frenetic, writhing arena where particles and antiparticles spontaneously appear and vanish in fractions of a second. This isn't theoretical, we've measured it. Place two metal plates incredibly close together in a vacuum, and you'll detect a faint pressure between them. That's the Casimir effect, hard proof that even in the deepest void, reality is anything but quiet. What we call nothingness is more like a simmering pot of water, with bubbles of matter and energy constantly forming and popping. This quantum frenzy opens a startling possibility. If tiny particles can blink into existence briefly without breaking the laws of physics, could an entire universe do the same? Physicists like Alexander Vilenkin propose that our cosmos might be the ultimate quantum fluctuation, a bubble of spacetime that, against all odds, didn't immediately collapse back into nothingness. Think of it like a cosmic lottery where the jackpot is existence itself. Most quantum events cancel out instantly, but under the right conditions, perhaps a peculiar twist in the fabric of reality, one fluctuation could have tipped the scales, unleashing the chain reaction we call the Big Bang. What makes this idea so compelling is that it doesn't require any pre-existing material or energy. Quantum mechanics allows for temporary violations of energy conservation, as long as they're fleeting. In this view, the universe borrowed its energy from the void, with gravity providing the negative balance needed to keep the books balanced. It's as if the cosmos signed a check to itself, creating matter and antimatter in equal amounts while gravity tallied the debt. Over billions of years, the expansion of space stretched that initial quantum spark into the vast web of galaxies we see today. Critics argue this just kicks the can down the road, what caused the quantum fields to exist in the first place. But supporters counter that at this level, cause and effect might not operate as we know them. The physicists' nothing isn't philosophical emptiness. It's a roiling quantum vacuum where the distinction between something and nothing blurs. If particles can emerge without cause, perhaps universes can too. This reshapes the entire conversation. Instead of seeking a first cause, we might be looking at a self-sustaining cycle where reality flickers in and out of being, with our universe as one particularly lucky roll of the dice. The implications are staggering. If quantum fluctuations can birth universes, ours might not be unique. An endless multiverse could be frothing into existence right now, each bubble governed by different random parameters. Most might collapse instantly, but some where the numbers align just right could blossom into full-fledged cosmic landscapes. This transforms the question from, why is there something rather than nothing? To, why does anything ever stop happening? In the quantum realm, nothingness isn't a dead end, it's a launch pad. Heisenberg's uncertainty principle reveals a universe that refuses to sit still, even in perfect emptiness. At scales smaller than atoms, particles and antiparticles constantly flicker into existence, borrowing energy from the void before vanishing again in a cosmic game of hide and seek. These aren't just mathematical quirks, we've measured their effects. The entire universe might owe its existence to this restless quantum activity, where nothing is never truly empty. 0-point energy, the lowest possible energy state of a quantum system, is anything but zero. Picture a guitar string that can never stop vibrating, no matter how perfectly you mute it. Space itself behaves like that, humming with imperceptible activity. This isn't just background noise, it's the foundation of reality. Some theories suggest that under the right conditions, this quantum jitter could have tipped the scales, transforming a fleeting fluctuation into a self-sustaining universe. Imagine a single bubble forming in a boiling pot, but instead of popping, it expands exponentially, a microscopic event snowballing into cosmic proportions. The math behind this is staggering. Quantum fields permeating the void can briefly concentrate energy, warping spacetime enough to create a self-contained pocket. Most collapse instantly, but if conditions align perhaps through a phenomenon called quantum tunneling, one could escape annihilation. Like a ball spontaneously rolling over a hill it shouldn't have the energy to cross, the universe might have tunneled into existence from a state of non-existence. This turns traditional causality on its head. The cosmic egg wouldn't need an external trigger, just the inherent instability of quantum nothingness. Critics argue this merely replaces one mystery with another. What governs the quantum fields that allow such fluctuations? But proponents counter that at these extremes, our everyday logic fails. Time, space, and even the concept of before might emerge from the universe's birth, making the question of cause meaningless. The 0-point void isn't passive, it's a generative froth where reality constantly tests its own boundaries. This reshapes how we view creation. Instead of a singular, definitive beginning, the cosmos might be one episode in an endless cycle of quantum genesis. Other universes could be budding right now in some unimaginable meta-void, each with different physical laws. Most would fizzle instantly, but statistically, a few would stabilize a staggering thought that makes our existence feel both miraculous and inevitable. The quantum vacuum isn't sterile ground, it's fertile soil where universes take root. The idea of cosmic inflation hits like a lightning bolt, a revelation that reshaped our entire understanding of the universe's first moments. Picture this, a fraction of a second after the Big Bang, space didn't just expand, it exploded, stretching from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. This wasn't gradual growth, it was a runaway cosmic sprint, doubling in size over and over again at speeds that defy intuition. Physicist Alan Guth proposed this wild idea in 1980, not to explain the universe's birth, but to solve a puzzle. Why does the cosmos look so eerily uniform in every direction? Inflation answers that with elegance. Imagine blowing up a balloon with tiny dots on its surface. As it inflates, dots that were once close together drift far apart, yet the pattern stays smooth. No clumps, no empty patches. That's what happened to space itself. Regions too distant to ever interact somehow share identical temperatures and densities because they were once neighbors, stretched apart by inflation's relentless push. This also explains why we don't see cosmic defects like tangled spacetime or leftover magnetic monopoles. Inflation stretched them so thin they effectively vanished. But here's where it gets thorny. If inflation smoothed everything out, what started it? Guth's original proposal pointed to a bizarre quantum field called the inflaton, a sort of cosmic adrenaline rush that sent space into hyperdrive. The leading theory suggests this field got temporarily stuck in a high-energy state, like a ball perched on a plateau, before suddenly rolling downhill. As it rolled, it released energy that heated the universe, creating the hot soup of particles we call the Big Bang. But the real shocker, that initial stuck state, might have been a random quantum fluctuation in an otherwise empty void. This flips the script entirely. Instead of needing some grand, pre-existing cause, inflation could have been sparked by a microscopic blip, a tiny burp in the quantum foam that snowballed into reality. Some models even suggest that what we call the Big Bang was just the end of inflation, the moment the inflaton field's energy transformed into matter and radiation. It's a dizzying thought. Our vast universe might owe its existence to a quantum hiccup in a realm where nothing was the only rule. Critics pounce on the loose ends. What determines the inflaton's properties? Why did it decay in just the right way to produce a universe like ours? And most hauntingly, if inflation can start once, could it happen endlessly, spawning countless universes with different laws of physics? This is the multiverse hypothesis, where our cosmos is just one bubble in an infinite froth of inflationary events. Guth himself called it the ultimate free lunch, a self-replicating process where universes beget more universes, with no need for an external trigger. The beauty of inflation is how it turns mysteries into stepping stones. It explains the universe's smoothness, its flat geometry, even the seeds of galaxy formation, all while pointing toward deeper questions. But perhaps its greatest gift is humility. However confident we are about cosmic history, the first sliver of a second remains a frontier where physics as we know it falters. Inflation isn't the final answer. It's a bridge between the known and the unknowable, reminding us that the universe's origins might be stranger than any story we've yet dared to tell. Bouncing cosmology turns the Big Bang into a cosmic heartbeat, an endless rhythm of collapse and rebirth where universes don't begin from nothing, but rebound from the ashes of their predecessors. Picture a rubber ball dropped from space, compressing until it can't squeeze further, then exploding back outward. Now imagine that ball is all of reality, crushed to a point so dense that time and space warp beyond recognition, only to spring forth anew. This isn't just poetic imagery, it's a serious theory championed by physicists like Paul Steinhardt and Neil Turok, who argue that the singularity of the Big Bang might not be a true beginning, but a pivotal moment in an infinite cycle. What makes this idea so compelling is how it sidesteps the thorny question of absolute origins. No need for quantum fluctuations or divine sparks, just an eternal dance where each universe's death becomes the next one's cradle. The math behind it is breathtaking. As a contracting universe nears its crunch, quantum effects could generate a repulsive force strong enough to reverse collapse into expansion. Think of it as cosmic CPR, where the very laws of physics perform chest compressions to revive spacetime. But the elegance comes with puzzles. If each cycle reboots the cosmos, why doesn't entropy, the universe's tendency toward disorder, pile up over time? Some models suggest that during the bounce, matter and energy are utterly remixed, resetting entropy like a shuffled deck of cards. Others propose that dark energy, the mysterious force accelerating today's expansion, might cleanse the cosmic slate by diluting remnants of previous cycles into oblivion. The real stumper, though, is the cycle's own origin. even if universes can bounce endlessly, what set the rhythm in motion? Proponents argue that asking, what came before the first bounce, might be like asking what's north of the North Pole. The question dissolves in the geometry of reality. But skeptics counter that without evidence of prior collapses, the theory risks replacing one mystery with another. Yet bouncing cosmology leaves us with a profound shift in perspective. If true, the Big Bang wasn't a singular miracle, but part of an infinite lineage. Those distant galaxies racing away from us, they're not fleeing toward nothingness, but perhaps toward a future rendezvous where everything converges, only to begin again. It's a vision that transforms creation from a one-time event into an eternal refrain, a universe that breathes. String theory paints a picture of reality so bizarre it makes quantum fluctuations look tame. Imagine every particle in the universe isn't a dot, but a tiny, vibrating string like microscopic guitar strings playing the symphony of existence. The pitch of their vibration determines whether they become quarks, electrons, or photons. But here's the twist: these strings don't just wiggle through the 3 dimensions we know. They dance through 11 dimensions, most curled up so tightly we'll never perceive them. This isn't science fiction, it's a leading candidate for the theory of everything, attempting to unite gravity with quantum mechanics. Within this framework, the concept of a multiverse isn't just possible, it's practically inevitable. Think of those extra dimensions as hidden valleys in a vast cosmic landscape, each with its own unique terrain. Some valleys might have physics like ours, with stars and atoms. Others could be so alien that matter instantly unravels or time flows backward. When a pocket of this landscape stabilizes, it might inflate into a full-fledged universe, one bubble in an endless froth of realities. Our cosmos, then, isn't special. It's just one possible configuration in an unfathomably diverse ensemble. But this raises a thorny question. If string theory's multiverse explains why our universe has its particular laws, by sheer probability among infinite variations, does it really solve the mystery of existence or just kick it upstairs? Instead of asking why this universe came from nothing, we're now asking why any universe emerges from the string landscape. Some argue this is progress, that nothing we're dealing with is richer, a realm of mathematical potentiality rather than sheer void. Others counter that without a mechanism to generate the landscape itself, we've just swapped one enigma for another. The debate cuts to the heart of modern physics. Are we uncovering deeper layers of reality, or are we building ever more elaborate stories to avoid confronting the ultimate unknown? String theory's allure is its mathematical beauty, but after decades it still lacks experimental proof. The multiverse might be a thrilling possibility, or it might be a cosmic Rorschach test revealing more about our desire for answers than the universe's true nature. Yet even as skeptics question its testability, string theory reshapes how we envision creation. Those vibrating strings don't just compose matter, they might encode spacetime itself, turning the Big Bang from an explosion in space to the birth of space. In this view, universes don't emerge into anything. They're self-contained structures where dimensions unfurl like petals. The nothing before our universe could be a higher dimensional void where the very concept of before has no meaning. This is where physics blurs into metaphysics. If the multiverse is real, then every possible universe exists somewhere in the landscape, rendering our existence statistically inevitable. But if every possibility is realized, does why even matter? The search for origins might boil down to accepting that in an infinite ensemble of realities, universes like ours simply happen. Not because of a grand design, but because in the endless permutations of string vibrations, our particular tune was bound to play at least once. Perhaps the most humbling insight isn't about other universes, but about our place in the cosmic puzzle. String theory suggests that what we call the laws of physics might just be local bylaws rules that apply in our neighborhood of the multiverse. The deeper truth could be that existence isn't fine-tuned. It's unfathomably varied, with our universe's life-friendly conditions being one roll of the dice in a game with infinite throws. This doesn't answer why there's a dice game at all, but it transforms the question from why is there something rather than nothing to why does the something we see take this particular form? And that shifter from absolute origins to structural explanation might be the closest we get to understanding reality's deepest layers. After all, if the multiverse is real, then nothingness isn't empty. It's a fertile ground where every possible universe is waiting to happen. Take the screen you're watching right now, every color, every shape, every moving pixel. Now imagine all that information could be compressed into a flat, two-dimensional surface without losing a single detail. That's the essence of the holographic principle, a theory so radical it suggests our three-dimensional universe might be nothing more than an incredibly convincing projection. According to this mind-bending idea, all the information needed to describe every star, every planet, and even your own thoughts could be encoded on a distant cosmic boundary, like a movie stored on a Blu-ray disc. What we experience as depth, texture, and movement might just be nature's ultimate optical illusion. This isn't just wild speculation. The math actually checks out. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind stumbled onto a startling discovery while studying black holes. They realized the information swallowed by these cosmic monsters didn't vanish. It got smeared across their event horizons, the invisible one-way gates where gravity becomes inescapable. Stranger still, the amount of data that could fit on a black hole's surface matched the volume inside perfectly, like a cosmic ZIP file with no compression loss. If a black hole's entire interior could be described by information on its edge, why not the universe itself? The implications rewrite our understanding of reality's origins. If the holographic principle holds, then the Big Bang might not have been the birth of matter and energy, but the boot up of a cosmic computer. What we call nothing could be a vast, dormant network of quantum bits, a frozen code waiting to execute. In this view, the universe didn't emerge from emptiness, but from a latent information structure flickering to life. Think of it like a video game world loading into existence. The mountains, the rivers, the characters aren't made in that moment. They're simply rendered from pre-existing data. Critics argue this swaps one mystery for another. Who or what wrote the cosmic code? But supporters counter that the holographic principle doesn't require a programmer. It suggests information might be the fundamental currency of reality, more basic than space or time. Just as water can exist as ice, liquid, or vapor, existence might have different phases, with our universe being one particularly vivid state of information. This reframes the search for cosmic origins entirely. Instead of hunting for the particle or force that sparked creation, we might be deciphering the rules of a cosmic programming language. The equations governing quantum gravity could be nature's source code, and the Big Bang the moment those lines began running. It's a vision where physics meets computer science, and where nothing isn't empty space, but the blank screen of a universe not yet rendered. The holographic principle does more than challenge our perceptions. It redefines what we mean by real. If the depth and texture of our world are projected from some distant, flat archive, then reality is less like a sculpture and more like a shadow puppet show, with the true action happening somewhere we can't see. It suggests that at its core, existence might not be about stuff at all, but about relationships, the way information dances and interacts to create the illusion of substance. Perhaps most tantalizing is how this idea bridges the microscopic and the cosmic. The same quantum weirdness that lets particles be in two places at once might scale up to the universe itself, treating all of spacetime as a quantum hologram. If true, then every law of physics, every constant of nature, could be emergent properties, not fundamental truths, but the way our particular projection happens to run. The holographic principle doesn't just offer a new origin story. It suggests we've been reading reality's surface all along, while the real story was written in invisible ink at the edges of perception. While string theory adds extra dimensions to the cosmic equation, loop quantum gravity takes a radically different approach. It rewrites the rules of spacetime itself. Picture the fabric of reality not as a smooth continuum, but as an intricate web of interconnected loops woven so tightly that space and time become granular at the smallest scales. These aren't physical threads, but fundamental building blocks, tiny quantum knots where gravity and geometry fuse into something entirely new. According to this theory, when you zoom in far enough, the universe resolves into a shimmering lattice of these loops, like pixels on a screen revealing reality's true resolution. This changes everything about how we imagine the Big Bang. Instead of a singularity, a point of infinite density where physics breaks down, loop quantum gravity proposes something far stranger. The universe before the bang wasn't nothingness. It was a previous cosmic era squeezed to its quantum limit. Imagine a spring compressed to the absolute maximum. Just when it seems it can't get any smaller, quantum effects kick in, generating a repulsive force so powerful it reverses the collapse. The Big Bang becomes the Big Bounce, a cosmic rebound where time, space, and matter get a second act. The math behind this is breathtaking. In standard physics, gravity grows infinitely strong as matter gets denser, leading to the singularity problem. But loop quantum gravity introduces a built-in safety valve, a point where gravity flips from attractive to repulsive due to quantum corrections. It's as if the universe hit a quantum speed bump, bouncing back rather than crushing itself into oblivion. This means the pre-bang universe could have been a mirror image of our own, contracting rather than expanding, but governed by the same fundamental laws. Yet for all its elegance, the theory leaves one haunting question unanswered. What set the cycle in motion? If each universe springs from a previous collapse, where did the very first iteration come from? Some theorists suggest the question might be meaningless, that time itself could be circular, with no true beginning or end. Others propose that quantum fluctuations in some deeper reality seeded the initial conditions. But the real revolution here is conceptual. Loop quantum gravity doesn't just tweak our origin story, it erases the idea of absolute nothingness entirely. The void we imagined before creation might have been a seething quantum foam, where spacetime constantly rearranges itself into new configurations. What makes this so compelling is how it reframes existence. The universe isn't a one-time event, it's a phase in an endless dance of expansion and contraction. Those distant galaxies racing away from us might one day slow, reverse course, and eventually collide in a fiery cruncher only to rebound anew. It's a vision both humbling and exhilarating, suggesting that creation isn't a singular miracle, but a rhythm written into the very fabric of reality. Still, the theory faces fierce challenges. Unlike string theory's mathematical elegance, loop quantum gravity's equations are notoriously difficult to solve, making testable predictions scarce. And while it banishes the singularity, it doesn't fully explain why our universe has the precise physical constants needed for stars, planets, and life. But perhaps its greatest contribution is philosophical. By treating spacetime as something that emerges from deeper quantum relationships, it hints that the ultimate answer to where did the universe come from might not lie in some primordial event, but in the timeless rules that govern how existence stitches itself together. In the end, loop quantum gravity offers neither a beginning nor an end, just an infinite cosmic heartbeat, pulsing to a quantum rhythm we're only beginning to decipher. Whether this vision holds up or not, it reminds us that the universe's origins might be stranger and more beautiful than we ever imagined. While physicists crunch equations to pin down cosmic origins, philosophers have wrestled with nothingness for millennia, and their insights might hold keys science hasn't considered. Jean-Paul Sartre famously declared that existence precedes essence, meaning we're thrust into being without predefined purpose. But beneath that idea lies something profound, his concept of l'néant, the nothingness that haunts human freedom. For Sartre, emptiness isn't just absence. It's the gap between what is and what could be, the fertile void where possibility takes root. Imagine standing at a cliff's edge, feeling both dizzying freedom and terror because nothing determines your next step. That existential nothingness mirrors the quantum vacuum, a seething potentiality where reality constantly negotiates its own boundaries. Taoist philosophy flips the script entirely. Where Western minds often separate being from non-being, the Tao Te Ching proclaims, the wheel's usefulness comes from the emptiness at its hub. Here, void isn't opposite to form, it's its necessary counterpart, like the hollow inside a cup that makes it functional. Picture a whirlpool in a river. Is the swirling water the something and the center hole the nothing? Or are they two faces of one phenomenon? This ancient insight eerily anticipates modern field theories, where particles are excitations in an underlying quantum field, the peaks and troughs of an invisible ocean where empty space is the medium. Buddhism takes it further with sunyata, often translated as emptiness. But this isn't nihilistic void, it's the realization that all phenomena lack independent existence, arising only through interconnected causes. Think of a rainbow, vivid yet impossible to grasp, existing only because of sunlight, droplets, and perspective. In this view, asking whether the universe came from nothing might miss the point. Perhaps things are just temporary patterns in a dynamic flow. Modern cosmology's discovery that matter is frozen energy echoes this 2,500-year-old intuition that form is ephemeral. These perspectives collapse the clean divide between nothing and something. Quantum physics shows particles popping into existence. Existentialism frames nothingness as creative ground. Eastern thought sees form and void as inseparable as ink and paper. Science traditionally treats nothing as a neutral background, the blank stage where matter performs. But what if nothing is the actor too? The Hindu concept of Brahman, an ultimate reality beyond being and non-being, aligns with quantum physicist David Bohm's implicate order, a deeper layer where existence and potential are folded together like a cosmic origami. Perhaps the most radical idea comes from process philosophy, which views reality as perpetual becoming rather than static being. Imagine a movie projected frame by frame. The nothing between frames isn't dead space but the necessary interval for change. In this light, the Big Bang wasn't a transition from nothing to something, but from potential to actualization, like a seed unfurling into a tree. The equations might describe how, but philosophy keeps asking why and whether our either-or categories are illusions. After all, even in nature, the richest soil appears black because it's teeming with life too small to see. Nothingness, it seems, was never empty. What if consciousness isn't just a product of the universe, but its very foundation? This mind-bending idea emerges from quantum mechanics' strangest quirk, the observer effect. In the famous double-slit experiment, particles behave as waves when unobserved, spreading out in probabilities. But the moment a scientist measures them, they snap into definite positions, as if reality solidifies under our gaze. Nobel laureate Eugene Wigner took this further, suggesting consciousness itself might collapse quantum possibilities into actual events. Extend that idea to cosmic scales, and you're left with a staggering possibility. Could the universe have needed a first observer to spring from nothingness into being? This isn't mystical speculation, it's a frontier where physics brushes against metaphysics. John von Neumann, the mathematical genius behind quantum theory's formal structure, proposed that the entire universe might be one vast quantum system waiting for observation. In this view, the Big Bang wasn't just a physical event, but a kind of cosmic measurement, a moment when infinite potential crystallized into concrete reality. Picture a dreamer waking from a dream, except the dreamer is existence itself, and the act of waking is what creates time, space, and matter. Critics argue this risks confusing correlation with causation. Just because consciousness affects quantum systems doesn't mean it created them, but supporters counter that at the universe's birth, the distinction between observer and observed might dissolve. If reality at its core is quantum information, then observation could be the process that decodes that information into the world we know. The physicist Amit Goswami frames this as monistic idealism, the notion that consciousness isn't inside brains, but brains are inside consciousness, like whirlpools in a universal stream of awareness. The implications rewrite the origin story entirely. Instead of asking how matter arranged itself into thinking beings, we'd be asking how thinking beings imagined matter into arrangement. Ancient Vedic texts described Brahman as consciousness dreaming the universe, a metaphor that now finds echoes in quantum theory. Even the holographic principle aligns here. If our 3D world is projected from 2D information, could consciousness be the projector? Yet hard questions remain. Who or what observed the first quantum fluctuation? Some theories suggest self-referential loops, where the universe observes itself into existence through its own emergent complexity. Others propose a cosmic version of the Anthropic Principle. Universes that don't generate observers never solidify, leaving only those where consciousness and cosmos co-create each other. It's a hall of mirrors where cause and effect blur, and the distinction between creator and creation melts away. Whether this theory holds or not, it forces us to confront a profound shift in perspective. For centuries, we've treated consciousness as a latecomer to an already mechanical universe. But what if we've had it backward? What if the universe is the latecomer, a shimmering mirage in an ocean of primordial awareness? The answer might lie not in telescopes or particle colliders, but in the very act of questioning itself, the universe peering back at its own origins through human eyes. Imagine the universe as a marble resting on the edge of a cosmic bowl, stable for now, but one nudge away from rolling into oblivion. This isn't just a metaphor, it's the spine-chilling premise of vacuum decay, where our entire reality might be balancing precariously on a false foundation. Physicists call it the false vacuum state, a seemingly stable arrangement of quantum fields that's actually metastable, like ice supercooled just below freezing, waiting for the slightest disturbance to shatter into liquid. Our universe could be in exactly this kind of temporary equilibrium, with every atom, every galaxy, every law of physics just a quantum hiccup away from dissolving into a lower energy, true vacuum. The math behind this is as elegant as it is terrifying. Quantum fields permeating space have specific energy levels like steps on an infinite staircase. We think we're standing on solid ground, but we might actually be perched on a high step, a false plateau. If some random quantum event knocks the universe off this ledge, a bubble of true vacuum could form at light speed, rewriting the very rules of existence as it expands. Inside that bubble, the constants we rely on, the strength of gravity, the mass of electrons, might change instantly. Chemistry as we know it would cease. Stars would wink out. Life as we understand it would become impossible, not through destruction, but through a fundamental redefinition of what possible means. What makes this theory so haunting is its symmetry to cosmic origins. Just as our universe might have emerged from a quantum fluctuation in nothingness, it could vanish the same way, not with a bang, but with a silent reconfiguration. The Higgs field, which gives particles mass, is particularly suspect. Its current energy state appears fine-tuned, too perfectly balanced to be accidental. Some theorists argue this suggests we're in a precarious state, like a pencil standing on its tip, destined to eventually fall. The only reason we haven't seen vacuum decay yet. On cosmic timescales, 13.8 billion years might be the blink of an eye before the inevitable tumble. But here's the twist: vacuum decay isn't necessarily the end. A true vacuum state might birth an entirely new universe with different physical laws, a cosmic phoenix rising from the ashes of our reality. This transforms the idea of nothingness from passive emptiness to an active threshold, where existence constantly reinvents itself. The chilling part: if a decay bubble forms anywhere in the cosmos, we'd never see it coming. At light speed, the wave of annihilation would erase all evidence of itself as it goes, leaving no trace and no witnesses behind. This isn't science fiction. We've actually created false vacuum states in labs, tiny, fleeting pockets where quantum fields get stuck in higher energy configurations. The Large Hadron Collider constantly monitors the Higgs field for signs of instability. So far, so good, but the universe is vast and quantum events are random. Given enough time, statistical inevitability might take its toll. Vacuum decay forces us to confront an uncomfortable truth. The universe might not just have come from nothing. It might return to nothing, or rather, to a new kind of something we can't comprehend. It's the ultimate cosmic irony. The same quantum instability that could have sparked existence might one day erase it, leaving no record that we, or any of this, ever were. Yet within that fragility lies a strange comfort. If reality is this delicate, then every moment of existence becomes staggeringly precious, a temporary spark in the void, shining against all odds. Dark energy is the universe's greatest unsolved riddle. An invisible force pushing galaxies apart faster than gravity can pull them together. Imagine blowing up a balloon with tiny dots on its surface, only to watch the dots not just drift apart but accelerate as if the balloon had a mind of its own. That's the baffling reality astronomers confronted in the late 1990s when distant supernova revealed cosmic expansion wasn't slowing down as everyone expected, but speeding up. The culprit, a mysterious something dubbed dark energy, making up 68% of the universe's total content. But here's the twist: we have no idea what it actually is. Some theories suggest dark energy might be the cosmological constant. Einstein once proposed a property of empty space itself, where the vacuum isn't truly empty but brimming with latent energy. Others speculate it's a dynamic field, like the inflaton that drove the universe's early exponential growth. But with a sinister twist: instead of fading, this field grows stronger over time. But the most mind-bending possibility: dark energy could be a relic of the primordial void, a ghostly fingerprint of whatever nothingness existed before the Big Bang. Picture an echo reverberating through time, where the absence that once birthed the universe now stretches it toward an uncertain fate. This idea flips our understanding of nothingness on its head. Instead of being a passive backdrop, the void might actively shape cosmic evolution. Think of it like a river carving a canyon. The absence of rock is what gives the water its power to sculpt. Similarly, dark energy could be the universe's way of remembering its origins, with the void's influence lingering like a shadow in the equations of space-time. If true, it means creation and destruction aren't separate events, but two sides of the same coin. The same quantum froth that birthed galaxies might one day tear them apart. The stakes couldn't be higher. Depending on dark energy's true nature, the cosmos could face radically different futures. If it's a constant force, expansion will continue steadily, leaving galaxies isolated in a cold, dark expanse. If it strengthens over time, the universe might rip itself apart atom by atom in a big rip. Or if we're spectacularly lucky, dark energy could weaken, allowing gravity to eventually reverse expansion into a big crunch. Each scenario hinges on whether this enigmatic force is a static feature of reality or a dynamic remnant of the void, still evolving like a cosmic hourglass counting down. What's haunting is how little we know. Dark energy doesn't interact with light or matter. It's detectable only through its gravitational bullying. Upcoming telescopes like the Vera Rubin Observatory and the Euclid space mission aim to map its influence with unprecedented precision, hunting for clues in the large-scale structure of the universe. But until then, we're left with a profound irony. The force dominating the cosmos might be the closest thing to nothingness we've ever encountered. Perhaps that's the ultimate lesson. The void isn't just where the universe came from, it might be the hand guiding its destiny. From the quantum fluctuations that sparked existence to the dark energy now stretching space-time thin, nothingness isn't passive. It's the silent architect of reality, weaving creation and destruction into a single, unbroken story. And if that's true, then the answer to where we're headed might lie in understanding where we began, not in the glare of the Big Bang, but in the quiet dark that came before. Black holes might be more than cosmic vacuum cleaners. They could be the ultimate cosmic nurseries. Theoretical physicist Lee Smolin proposed a radical idea. Every black hole's crushing core doesn't end in a singularity, but becomes the seed for an entirely new universe. Picture a Russian nesting doll where each doll contains another, smaller one inside, except in this case, each doll is a universe with its own laws of physics, birthed from the gravitational collapse of a dying star in its parent cosmos. Smolin's theory, called cosmological natural selection, suggests a process eerily like biological evolution. Just as mutations create slight variations in DNA, black holes might tweak fundamental constants when spawning new universes. A universe that produces more black holes by having physics finely tuned for star formation and collapse would effectively have more offspring. Over infinite cycles, universes would evolve toward optimal black hole production, explaining why our cosmos seems so perfectly calibrated for their creation. It's cosmic Darwinism on the grandest scale, where survival of the fittest applies to the laws of nature themselves. But this elegant idea hits a familiar wall. If universes arise from black holes, what created the very first one in the chain? Smolin's model replaces the mystery of a singular Big Bang with an infinite regression of cosmic generations, each universe born from a black hole in its predecessor. Yet even an infinite lineage can't escape the root question. How did the initial ancestor emerge from nothingness? Some interpretations suggest the first universe might have arisen from a quantum fluctuation in an eternal void, making the entire multiverse a self-sustaining loop with no true beginning or end. Critics argue this merely postpones the hard problem. Without evidence of other universes or observable changes in physical constants, the theory remains speculative. But supporters counter that black hole singularities where our current physics breaks down are precisely the places where new physics and perhaps new universes could take shape. The math hints at this possibility. When matter collapses beyond the event horizon, equations suggest space-time curvature becomes infinite, which might not signal destruction, but a transformation, a bridge to another reality. What's fascinating is how this reshapes our view of black holes. Rather than dead ends, they become cosmic wombs. The violent death of a star in our universe could be the fiery birth of another cosmos with slightly different rules. Over eons, universes might evolve toward conditions that favor life, not by design, but because life-friendly physics also tends to produce more black holes. It's a hauntingly beautiful vision. We might owe our existence to countless ancestral universes that lived, died, and birthed successors in their graves. Yet the lingering question remains whether the chain stretches back infinitely or not. The ultimate origin still whispers from the shadows. If universes can create themselves through black holes, does nothingness even have meaning anymore? Or is the void itself a kind of fertile ground, where the distinction between something and nothing blurs into irrelevance? Smolens's theory doesn't just challenge our understanding of cosmic origins, it forces us to reconsider whether beginnings and endings are illusions, and if reality is less a linear story than an endless dance of creation and transformation. Max Tegmark's mathematical universe hypothesis turns reality inside out. What if the stars, the planets, even your morning coffee aren't made of matter at all, but of numbers? Not as metaphors, but as the literal fabric of existence. Picture a flawless geometric equation so vast and intricate that its solutions are the universe, every particle a symbol, every force a relationship between variables. In this view, the Big Bang wasn't an explosion of energy but the first step in a cosmic calculation, unfolding according to immutable mathematical rules. The strangest part, if true, it means nothing physical ever needed to be created at all. The universe isn't a thing, it's a timeless truth waiting to be computed. This idea didn't spring from mysticism, but from a glaring pattern in physics. Every fundamental law we've discovered, from Einstein's gravity to quantum mechanics, is written in mathematics. Not approximately, but with eerie precision. When physicists probe the deepest layers of reality, they don't find tiny machines, they find equations. Even particles behave less like objects and more like solutions to wave functions. Tegmark takes this to its logical extreme. If math describes reality perfectly, maybe it is reality. The implications are dizzying. A black hole singularity isn't a place where physics breaks down, it's where the equation becomes undefined. The quantum foam isn't chaotic, it's a fractal expression of deeper numerical relationships. But here's the rub. If the universe is just math, why does it feel so tangible? Why do we experience the warmth of sunlight or the weight of stone? Tegmark suggests these sensations are the universe's way of rendering abstract structures to conscious observers like us. Think of a video game. The sword in your hand isn't really metal, it's data interpreted by the software. Similarly, our brains might be biological algorithms playing the mathematical universe, translating equations into the vivid theater of lived experience. This bridges Plato's ancient idea of a world of perfect forms with modern physics, where the tangible is just a shadow cast by numerical light. Critics pounce on a glaring question: where do the mathematical laws themselves come from? If existence is a tautology, a self-consistent structure needing no external cause, then why this particular set of equations? Some argue that all possible mathematical structures exist equally, making our universe just one page in an infinite textbook of realities. others counter that without a mechanism to select which equations become real, the theory explains nothing. But Tegmark's boldest claim is that these doubts stem from our anthropocentric bias. We keep searching for a material cause because we're trapped in the illusion that reality must be made of something. Math doesn't need to be built, it just is. The most haunting implication isn't about origins but meaning. If the universe is fundamentally abstract, then purpose and agency might be emergent illusions, stories we tell to navigate the equations. Yet there's a strange comfort in this austerity. Whether written in atoms or algorithms, the cosmos still composes galaxies, stars, and beings capable of awe. The equations, it seems, have a poetry of their own. Stephen Hawking's no-boundary proposal bends the mind like spacetime itself. What if the universe didn't have a starting point at all, but curved back on itself like a cosmic Ouroboros? Picture Earth's North Pole. There's no edge there, no boundary where the map stops. If you keep walking north, you don't fall off, you just start moving south. Hawking and physicist James Hartle applied this logic to time itself, suggesting that at the Big Bang, the dimension we experience as before loops back like a circle. The universe wouldn't explode from something. It would simply be a self-contained bubble of reality with no sharp edges in space or time. This isn't just poetic imagery, it's hard math. Hawking's equations merged quantum mechanics with general relativity, treating the early universe's timeline like a sphere's surface. Just as you can't ask what's north of the North Pole, you can't ask what came before the Big Bang in this model. The question dissolves into geometry. Imagine a light bulb flickering on. We see the glow, but the filament's heat has no single first moment. It's the whole circuit that matters. Similarly, the universe's origin might not be an event, but a seamless transition from imaginary time, a mathematical trick for handling quantum gravity to the arrow of time we experience. The brilliance of this idea is how it sidesteps the need for a creator or external cause. If time loops back, the universe becomes its own parent, a self-starting engine requiring no spark. Hawking likened it to asking what's south of the South Pole, a nonsensical question because the coordinate system wraps around. Critics argue this swaps one mystery for another. How does time acquire its looped structure? But supporters counter that quantum gravity demands such weirdness. At Planck scales, spacetime becomes probabilistic, more like a cloud of possibilities than a rigid grid. What's haunting is how this reshapes nothingness. Instead of an empty void, Hawking's nothing is the absence of boundaries, a reality so complete it needs no outside. The universe doesn't emerge from nothing. It is nothing in its purest, most self-contained form. This echoes Buddhist metaphysics, where emptiness isn't lack, but potential freed from edges. The cosmic microwave background might hold clues. If the sky's faint temperature variations match the no-boundary predictions, we could be staring at the fingerprint of a universe that never truly began, just eternally transformed. Yet the proposal leaves us with a tantalizing paradox. If time loops at the bang, does free will unravel in that cosmic knot? Are our choices just echoes traveling a closed circuit? Hawking shrugged off such concerns. In his view, the no-boundary condition simply defines reality's playing field, leaving the game's richness intact. After all, a sphere has no edges, but you can still chart infinite paths across its surface. Maybe existence works the same way, boundless but brimming with stories. Roger Penrose's vision of the cosmos reads like a grand, never-ending symphony, one where the final notes of each movement seamlessly become the opening bars of the next. His conformal cyclic cosmology proposes a breathtaking loop of existence. Universes don't just end, they transform. Picture an infinite series of cosmic eons, each stretching across billions of years, where the demise of one universe plants the seed for the next. At the heart of this radical idea lies a simple but profound observation. When a universe grows old and cold, its vast, empty expanse of nearly massless particles becomes mathematically indistinguishable from the hot, dense singularity of a Big Bang. It's as if the universe, in its final act, folds in on itself to begin anew. The mechanics of this rebirth hinge on black holes, those enigmatic destroyers that might also be cosmic midwives. As black holes slowly evaporate over unimaginable timescales, leaking energy via Hawking radiation, they leave behind a universe stripped down to its barest components, photons and gravitons wandering an ever-expanding void. But here's Penrose's twist. In this ultra-smooth, ultralight state, the universe loses all sense of scale. Without massive particles to define distance or time, the infinite future of one eon can geometrically match the infinitesimal starting point of the next. The end becomes the beginning, not through a violent collision or a quantum bounce, but through a quiet mathematical symmetry like a Möbius strip where the end is just another name for the start. Critics raise eyebrows at the audacity of this idea. If each eon's death spawns a new one, what set the very first cycle in motion? Penrose sidesteps the question elegantly. In a conformal framework, the chain might have no true beginning or end. Time becomes a circle so vast that asking what came before is like asking what's north of the North Pole. Yet even this elegant solution leaves gaps. Why do the laws of physics persist unchanged across eons? And where do the subtle imprints Penrose claims to find in the cosmic microwave background, the alleged fingerprints of a previous universe's black holes, fit into the picture? What's mesmerizing about Penrose's model is how it redefines nothingness. The void between eons isn't empty, it's a realm where the very concepts of something and nothing lose meaning. When particles lose mass and space loses scale, existence transitions into a state beyond our everyday logic. It's a vision that echoes Buddhist cosmology's wheel of time, where creation and dissolution are phases of an endless cycle, and the universe breathes in and out like a living thing. The most tantalizing clue might lie in the sky. Penrose and his collaborators argue that concentric rings in the cosmic microwave background, patterns dubbed Hawking points, could be the radiation signatures of supermassive black holes from a prior eon. If confirmed, these ghostly circles would be the first tangible evidence of a universe before our own. But the scientific community remains divided, with some attributing the patterns to statistical noise. The debate rages on, a reminder that even the most brilliant ideas must face the gauntlet of observation. Whether Penrose's cyclic cosmology holds up or not, it forces us to confront a staggering possibility. Our universe might be both ancient and newborn, heir to an infinite lineage of cosmic ancestors and progenitor of countless more. In this view, the Big Bang wasn't a singular explosion from nothingness, but a turning of the page, a moment where the ashes of one story became the ink for the next. And if that's true, then the deepest mystery isn't how something came from nothing, but how the cosmos learned to recycle itself so perfectly, again and again, without ever losing the thread of its own existence. The simulation hypothesis turns our cosmic origin story into something straight out of a sci-fi novel. What if the Big Bang wasn't the beginning of reality, but the startup screen of an unfathomably advanced computer program? Picture this: the vast expanse of galaxies, the dance of subatomic particles. Even your own thoughts might not be fundamental truths, but lines of code executing in a simulation so sophisticated we can't detect the seams. In this scenario, the nothingness before our universe wasn't emptiness, it was the dormant state of a cosmic computer, its processors idle until some higher dimensional programmer hit run. This idea gained mainstream traction when philosopher Nick Bostrom laid out his now famous trilemma. Either civilizations never reach technological maturity, they choose not to run ancestor simulations, or we're almost certainly living in one. The math is chillingly simple. If advanced civilizations exist and have the computing power to simulate conscious beings, the number of simulated minds would vastly outnumber biological ones. Statistically speaking, you're more likely to be an artificial consciousness in someone else's universe than a carbon-based life form in the real world. But how would this reshape our understanding of creation? If we're in a simulation, the laws of physics aren't fundamental truths, they're the algorithms the simulation uses to maintain consistency. The speed of light, a processing limit, quantum entanglement, data packets syncing across the cosmic network, even the mysterious fine-tuning of physical constants could be explained as default settings chosen by the programmers. The Big Bang becomes less like a cosmic explosion and more like initializing a new instance of a universe generating software. Some physicists take this further, suggesting glitches in our reality might reveal the digital scaffolding beneath. Ever experienced déjà vu or seen quantum particles behaving differently when observed? These could be artifacts of rendering limitations or optimization shortcuts in the code. There's even a hunt for potential pixels of spacetime tiny Planck scale units that might hint at a discrete computational structure to reality. Yet the simulation hypothesis has its own existential rabbit holes. If our universe is a simulation, what about the reality running it? Does that world also exist inside a deeper simulation, turtles all the way up, and who or what booted up the very first reality in the chain? The theory doesn't eliminate the mystery of origins, it just relocates it to another plane of existence. What's fascinating is how this modern myth mirrors ancient creation stories. Plato's allegory of the cave suggested we only see shadows of true reality. Hindu cosmology describes the world as Maya, an illusion masking deeper truths. Even Descartes pondered whether an evil demon might be simulating his perceptions. The simulation hypothesis is arguably the 21st century version of these timeless questions, wrapped not in theology, but in the language of computing and quantum physics. Could we ever prove we're in a simulation? Some scientists propose looking for computational signatures, mathematical patterns in cosmic rays, or anomalies in high-energy physics that might reveal the universe's underlying code. Others suggest creating our own perfect simulations. If we succeed, it dramatically increases the odds we're in one too. But perhaps the most haunting implication isn't about evidence, but meaning. If we're simulated beings, do our choices matter? The answer might lie in how seriously the programmers take their creations. After all, even a simulated consciousness that believes its real experiences joy, pain, and wonder just as vividly. At its core, the simulation hypothesis isn't just a theory about technology, it's a radical reimagining of what reality even means. The atoms in your hand, the stars overhead, the fabric of space-time itself might not be the foundation of existence, but the user interface for something far stranger. And if that's true, then the greatest cosmic joke might be this: we've been searching for the meaning of life in the wrong dimension all along. Consider the sheer unlikelihood of our universe's recipe. If gravity were slightly stronger, stars would burn out in a cosmic blink. If the weak nuclear force were a fraction weaker, hydrogen atoms wouldn't fuse, leaving the cosmos sterile. This razor-thin balance of constants isn't just curious, it's the foundation of everything we know. The Anthropic Principle confronts this puzzle head-on. Maybe the universe isn't fine-tuned for life. maybe life emerges because the tuning is just right. It's a cosmic version of the observer effect. We can only measure a universe that permits our existence, no matter how improbable. But this raises a thorny question: is our universe a one in a trillion fluke, or evidence of something deeper? One camp argues for divine fine-tuning, where physical constants reflect intentional design. Yet science thrives on natural explanations, leading others to propose a multiverse, an infinite ensemble of universes, each with random parameters. In this view, we don't inhabit a special cosmos. We're simply in one of the rare bubbles where chemistry, stars, and thinkers like us can arise. Statistically, improbable things become inevitable given enough attempts. A single lottery ticket has slim odds, but with trillions of tickets, someone hits the jackpot. The multiverse theory, though, has its own philosophical quicksand. If other universes are unobservable by definition, does the idea qualify as science or metaphysics? Critics argue it's a tautology. Explaining fine-tuning by invoking infinite unseen realms feels like solving a mystery by multiplying the unknown. Supporters counter that inflationary cosmology and string theory already hint at multiple universes, making the multiverse a predictive extension of existing physics, not just a convenient escape hatch. Meanwhile, a third perspective challenges the premise entirely. What if the constants couldn't be different? Theoretical physicist Max Tegmark suggests mathematical inevitability. The laws of physics might be the only self-consistent equations possible, leaving no room for variation. In this view, the universe isn't fine-tuned. It's locked into its parameters by the rigid logic of mathematical structure. No creator, no multiverse lottery, just an eternal truth playing out in 4 dimensions. The Anthropic Principle doesn't settle the debate, it reframes it. Instead of asking why the universe allows life, we're forced to confront what why even means in this context. Are we reading purpose into coincidence, or is coincidence itself a kind of purpose? The answer might hinge on whether we see existence as a singular masterpiece, a random stroke of luck, or one page in an infinite library of realities. Each option carries weight, but all circle back to the same awe, that against vanishing odds, we're here to ask the question at all. Time might be the most familiar part of our daily lives, yet at the quantum gravity frontier, it becomes the ultimate enigma. Picture a clock melting in a Dali painting. That's what happens to time when we try to peer past the Big Bang. In Einstein's relativity, time is woven into spacetime's fabric, but quantum mechanics treats it as an external backdrop against which particles dance. When these two theories collide at the universe's birth, time itself frays at the edges, leaving physicists asking, can causality exist without a clear before and after? This temporal paradox cuts to the heart of cosmic origins. If the Big Bang marked the emergence of spacetime, then asking, what happened before, is like asking what's north of the North Pole, a question that might lack any meaningful answer. Quantum gravity theories like loop quantum cosmology suggest time could have quantum properties, emerging from a deeper, timeless reality like temperature emerging from atomic motion. Imagine freezing water. The rigid ice appears static, but zoom in and molecules still vibrate. Similarly, what we perceive as time's flow might be the macroscopic echo of quantum processes we don't yet understand. The implications rewrite creation's rulebook. Without a clear timeline, the transition from nothing to something can't rely on cause and effect as we know it. Some models propose time crystallized during the universe's infancy, like water freezing into ice, with quantum fluctuations serving as the seeds. Others suggest time is fundamentally relational, a measure of change between objects rather than an independent stream. In this view, the universe didn't begin in time, but generated time as part of its structure, like a plant growing its own roots. String theory adds another twist. Higher dimensional brains colliding could have sparked our universe without requiring a before, since time in the higher dimensional bulk might operate differently. It's akin to bubbles forming in a boiling pot. Each bubble's internal time begins at its creation, independent of the pot's history. Meanwhile, causal set theory posits that time is discrete, advancing in tiny Planck-sized steps, with the early universe resembling a quantum dice game where causality emerges statistically from randomness. The real stumper is how any of this allows for the universe's breathtaking order. If time's origin was truly lawless, why does our cosmos display such precise regularity, from the orbits of planets to the ticking of atomic clocks? Some physicists speculate that time's arrow isn't fundamental but emergent, like the way ink disperses in water. The low entropy state of the early universe, that improbable concentration of order, might have imprinted directionality on time, making cause and effect seem inevitable in hindsight. This temporal tug of war leaves us with a haunting realization. Our intuition about beginnings might be profoundly limited. The universe could be more like a poem where the first word arises from the rhythm of the whole, rather than a machine needing a spark. If time is a tapestry woven by quantum threads, then nothingness wasn't an empty stage, it was the unspun yarn, waiting for the loom of existence to start turning. Entropy is the universe's silent clockmaker, the invisible force that gives time its arrow, its relentless forward march. Picture a shattered wine glass. The pieces never spontaneously reassemble because entropy demands disorder increases over time. Yet here's the cosmic paradox. If entropy always grows, why was the early universe so improbably ordered? The Big Bang didn't start with chaos. It began with near-perfect uniformity, a primordial soup so finely balanced that gravity could sculpt galaxies over billions of years. This is like finding a pristine sandcastle on a beach where every tide only erodes. It defies everything we know about how disorder evolves. Physicists call this the past hypothesis, the baffling observation that entropy was absurdly low at the universe's birth. To grasp how strange this is, imagine shuffling a deck of cards into perfect numerical order by random chance. The odds are astronomically tiny, yet that's essentially what the cosmos did. It started in a state of exquisite organization, as if someone had carefully arranged all matter and energy before letting the clock start ticking. This isn't just a quirk, it's the reason time has a direction at all. Without that initial low entropy state, the arrow of time wouldn't point anywhere, and cause and effect would unravel into chaos. So how did the universe cheat entropy's usual rules? One daring idea comes from quantum fluctuations. In the quantum foam, tiny regions can temporarily decrease entropy, like a gust of wind briefly pushing smoke back into a chimney. Most fluctuations fizzle out instantly, but under the right conditions, perhaps a random burp in the void, one could have tipped the scales, birthing a pocket of order vast enough to become our universe. It's a cosmic version of winning the lottery, where the jackpot is existence itself, but there's a catch. Even if a quantum fluctuation sparked our universe's low entropy state, why hasn't entropy reasserted itself sooner? Why did the universe have just enough order to last billions of years, allowing stars, planets, and life to form? This hints at something deeper, a fine-tuning so precise it strains coincidence. Some theorists propose a hidden principle, a law we haven't discovered yet that favors orderly beginnings. Others argue for the multiverse. In an infinite sea of universes, a few will inevitably hit the entropy jackpot by sheer statistics, and we're in one of those lucky bubbles. The most radical solution comes from cosmologist Sean Carroll, who suggests entropy's arrow might be an illusion, a local quirk of our cosmic neighborhood. Imagine standing at the crest of a hill between two valleys. Time flows downhill into higher entropy in both directions. From our perspective, we see only one slope, but the Big Bang could be the midpoint of a larger timeline where entropy decreases on the other side. In this view, our universe's orderly beginning isn't the start, it's the turning point of a grander symmetry, like a cosmic hourglass flipped halfway through. Yet all these explanations dance around the same haunting question. Why does anything remember the past? The universe's low entropy beginning isn't just a physical puzzle, it's what makes history possible. Without it, memories couldn't form, cause wouldn't precede effect, and existence would be an endless present with no narrative. In a way, entropy isn't just a property of the cosmos, it's the glue that binds our experience of reality. The fact that we can ask these questions at all might be the deepest clue that the universe's improbable birth wasn't an accident, but the first stroke of a story still being written. Quantum mechanics and Einstein's relativity are the twin pillars of modern physics, yet they speak entirely different languages. One governs the chaotic dance of subatomic particles, where probabilities reign and particles teleport through barriers. The other paints spacetime as a smooth, curving fabric where gravity emerges from geometry. For decades, physicists have struggled to reconcile these visions, knowing that their unification, a theory of quantum gravity, might finally explain how existence crystallized from the void. Imagine trying to merge a ballet with a mosh pit. The choreography seems impossible until you realize both are just expressions of deeper rhythms. The key lies in spacetime itself. According to general relativity, spacetime is dynamic. It bends, stretches, and ripples, but quantum mechanics insists everything, even gravity, must be quantized, meaning it comes in discrete packets rather than smooth flows. Picture a pond's surface. Relativity sees it as a continuous sheet disturbed by waves, while quantum theory suggests it's actually made of countless tiny droplets. The challenge: describe how those droplets arrange themselves into something that looks like a seamless fabric at larger scales. If we crack this, we might understand how space-time, and with it, the universe, emerged from whatever came before. Some theories suggest space-time isn't fundamental, but emergent, like temperature arising from the motion of atoms. In loop quantum gravity, space-time is woven from interconnected quantum loops, tiny threads of gravitational field that knot together to form the cosmic tapestry. At the universe's birth, these loops could have been so tightly tangled that the concepts of here and now had no meaning. The Big Bang, then, wouldn't be an explosion in space, but the moment these quantum threads unraveled enough to create space and time as we know them. It's as if the universe didn't appear within a void, but generated the void by untangling itself. String theory approaches the problem from another angle, proposing that particles, and even space-time, are vibrations of infinitesimal strings in higher dimensions. In this view, the Big Bang might have been a collision between cosmic brains, membranes floating in a higher dimensional bulk. The energy of that collision could have ignited our universe's expansion, with space-time emerging like a shockwave frozen into permanence. The eerie part: these theories imply that what we call nothing before the Big Bang might have been a higher dimensional arena our current physics can't describe. A place where time and space as we know them simply didn't apply. The most tantalizing clue lies in black holes. These cosmic paradoxes crush matter to a point where both quantum and gravitational effects dominate, offering a natural laboratory for quantum gravity. If space-time can be torn apart by a singularity, perhaps it was also stitched together by similar physics at the beginning. Some models suggest the Big Bang was the opposite of a black hole's collapse, a quantum bounce, where a previous universe's contraction flipped into our expansion, with space-time reconfigured in the process. Yet the ultimate mystery remains: how does structure arise from structurelessness? Quantum gravity might reveal that the void wasn't empty, but brimming with potential. A quantum foam where space-time constantly flickered in and out of existence until one fluctuation stabilized, nucleating our cosmos like an ice crystal forming in supercooled water. The phase change from nothing to something wouldn't need a cause in the traditional sense. It would be as natural as water freezing when temperatures drop. This shifts the entire conversation. Instead of asking how something came from nothing, we might be asking how order emerged from potential. The quantum void isn't a sterile blank slate. It's a seething network of relationships waiting to resolve into space-time. And if that's true, then the greatest magic trick of all wasn't the universe appearing from nowhere, but the infinite possibilities of quantum gravity collapsing into the single, shimmering reality we call home. Emergent space-time theories are turning our cosmic origin story inside out. What if the fabric of reality isn't woven from threads of space and time, but stitched together by something far stranger: quantum entanglement? Imagine the universe as a vast, interconnected neural network, where particles separated by billions of light years remain mysteriously linked, their fates intertwined faster than light could bridge the gap. This spooky action at a distance, as Einstein called it, might be more than just a quantum quirk. It could be the hidden scaffolding holding space-time itself together. The math behind this is as elegant as it is revolutionary. In the early 2000s, physicists discovered something astonishing. The equations describing entangled particles perfectly mirror those governing the geometry of space-time. It's as if two seemingly unrelated languages were secretly dialects of the same cosmic code. This led to the groundbreaking idea that entanglement isn't just happening within space-time. It might be what creates space-time. Picture a spider's web. The silk strands aren't the web, they're what give the web its structure. Similarly, space-time could emerge from a dense network of quantum connections, with every photon, electron, and quark subtly handshaking across the void to weave the stage we call reality. This reshapes how we think about the Big Bang. If space-time is emergent, then the universe's birth wasn't an explosion into emptiness. It was the moment a latent quantum network booted up, transforming potential into actuality. Think of a computer waking from sleep mode. The screen isn't built when you hit the power button. It's rendered from pre-existing circuits suddenly humming with electricity. In this view, the nothing before creation wasn't a void at all. It was an unactivated system, a cosmic motherboard awaiting its first spark. Support comes from black holes, those cosmic paradoxes where space-time breaks down. When matter falls into a black hole, it doesn't just vanish. Its information gets smeared across the event horizon like data encoded on a hologram. But here's the twist: that information remains entangled with radiation leaking back out. This suggests that space-time structure might be a kind of quantum error-correcting code, where entanglement stitches together regions that would otherwise drift apart. The Big Bang, then, could have been the moment this coding scheme reached critical complexity, flipping from chaos to coherence like a puzzle suddenly solving itself. Critics argue this swaps one mystery for another. How does entanglement, which requires particles to interact, exist before space-time provides the arena for those interactions? It's a chicken and egg problem that makes even seasoned physicists pause. But proponents counter that causality itself might be emergent. In the quantum realm, time's arrow can blur. Effects sometimes precede causes. Perhaps the universe didn't need a first moment in time. just a self-reinforcing loop of correlations that crystallized into the spacetime we know. The implications are staggering. If spacetime emerges from entanglement, then the distinctions between here and there, now and then, aren't fundamental. They're collective illusions, like the warmth we feel from molecules jostling in air. This could explain why the universe appears so finely tuned for life. The same quantum correlations that build spacetime might also favor structures capable of observation, like galaxies and conscious beings. It's a vision where the cosmos isn't just stranger than we imagined, it's stranger than we can imagine, with every atom, every star, and every thought arising from an invisible lattice of connections deeper than space itself. Yet the most haunting question remains: if spacetime is software running on quantum hardware, who or what wrote the program? The answer might lie in the mathematics. Some theories suggest the universe's rules aren't designed but inevitable, the only possible outcome of self-consistent logic. Others propose an infinite regression. Our universe's code runs on a deeper reality, which itself runs on something deeper still. But perhaps the truth is simpler. Maybe the universe isn't something that happened, it's something that happens, constantly reweaving itself from the bottom up, with every entangled particle adding another stitch to the tapestry of existence. In the end, emergent spacetime doesn't just change our origin story, it redefines what origin even means. The Big Bang wasn't a beginning, but a phase change, the moment an unseen quantum network flickered awake, dreaming the world into being. And if that's true, then the void before creation wasn't empty. It was pregnant with potential, humming with the silent music of connections waiting to be made. Philosophical naturalism stands as the bedrock of modern science, the unwavering commitment that every phenomenon, from falling apples to exploding stars, can be explained through natural laws without invoking the supernatural. Yet this very success confronts us with an unsettling frontier. While science brilliantly illuminates how nature operates, it remains stubbornly silent on why nature exists at all. Consider the laws of physics themselves, those elegant equations governing quantum fields and spacetime curvature. They describe reality with breathtaking precision, but they can't explain why those particular laws hold sway rather than others, or why there's any material reality for them to govern in the first place. It's like having a perfect instruction manual for building a house with no clue why the bricks or the blueprint exist to begin with. This isn't just an academic quibble, it's a crack in the foundation of our understanding. Take gravity, for example. We know masses attract inversely with distance squared, but why does that relationship persist across billions of light years? Why not an inverse cube law or no gravity at all? Science can trace gravity's effects back to the Big Bang, but the moment we ask why gravity, or any fundamental force, was present at that instant, we hit a wall. The late physicist Stephen Hawking once quipped that asking what came before the Big Bang is like asking what's north of the North Pole. Yet even this clever deflection acknowledges a deeper truth. Some questions might lie beyond science's reach, not because they're meaningless, but because they probe the preconditions for science itself to function. Here's where philosophy elbows its way into the lab. Metaphysical frameworks like modal realism suggest all possible universes exist equally, making ours just one page in an infinite library of realities. Others propose axiarchism, the idea that existence tends toward intrinsic value, so a universe like ours, capable of fostering complexity and consciousness, was somehow selected by an abstract principle of goodness. These aren't mystical claims, they're attempts to grapple with the brute fact of existence using reason rather than revelation. Even the hard-nosed physicist Richard Feynman admitted that the universe's most profound mystery isn't any particular phenomenon, but the sheer fact that it's here, ticking along in all its intricate glory. The tension between science and metaphysics isn't a weakness, it's a creative friction. When Nobel laureate Eugene Wigner pondered the unreasonable effectiveness of mathematics in describing nature, he wasn't invoking magic. He was highlighting how deeply strange it is that human logic aligns so perfectly with cosmic order. This convergence suggests that beneath the division between physics and philosophy lies a common substrate, the human drive to make sense of existence. Whether through equations or epistemology, we're all confronting the same primal wonder, that there's something rather than nothing, and that we're here to witness it. Perhaps the most humbling insight is that science's inability to explain its own starting point isn't a failure, but a reminder of its scope. Like a flashlight illuminating a dark room, natural explanations can only operate within a framework where nature exists. Asking why that framework holds in the first place might be like a character in a novel asking why the alphabet exists. The tools to answer lie outside the story itself. This doesn't mean we stop searching. It means we recognize that some horizons recede as we approach them, not because they're illusions, but because they mark the limits of one way of seeing. And in that recognition, science and philosophy don't compete. They conspire, each lending its unique lens to the grandest question of all. What does it mean for anything, including the laws of nature, to be? Language is both our most powerful tool and our most stubborn cage, especially when we try to describe the indescribable. Think about the word nothing. We use it every day, an empty cup, a blank page, but when applied to cosmic origins, it crumbles under its own weight. We say the universe emerged from nothing, but what does that even mean? Is nothing the absence of matter, the absence of space and time, the absence of physical laws themselves? Each layer strips the word further until we're left pointing at a concept our brains can't truly grasp, like trying to describe color to someone born blind. Philosopher Ludwig Wittgenstein saw this trap coming. He famously wrote, "The limits of my language mean the limits of my world," arguing that words can only map onto experiences we've actually had. But none of us have experienced true nothingness, no time, no space, no laws, so we're left stitching together approximations from scraps of language that don't quite fit. It's like trying to assemble a puzzle where all the pieces are from different boxes. When physicists talk about quantum fluctuations or false vacuums, they're not describing nothing as we intuitively understand it. They're describing a seething, mathematical somethingness that defies everyday language. Even the word universe trips us up. We instinctively picture it as a vast container, a cosmic fishbowl holding galaxies and stars. But if the Big Bang created space itself, there was no outside for the universe to expand into. Asking what's beyond the universe is like a character in a novel asking what's outside the book's pages. The question might feel urgent, but it's built on a flawed assumption that reality must always resemble the categories our language provides. This linguistic quicksand isn't just philosophical navel-gazing, it shapes the science itself. When cosmologists say the universe came from nothing, they're often referring to specific technical concepts like a quantum vacuum or a gravitational singularity that bear little resemblance to the colloquial nothing. The mismatch breeds confusion, leading some to imagine a magical creation ex nihilo, while others dismiss the idea as nonsensical. Both reactions miss the mark because the language itself is misfiring. So how do we move forward? Some theorists suggest borrowing from mathematics, where equations can express relationships without being shackled to physical metaphors. Others look to Eastern philosophies like Taoism, which grapple with non-being through poetry and paradox rather than rigid definitions. Even art offers clues. Abstract paintings or atonal music can evoke states that words can't capture, hinting at modes of understanding beyond literal description. The real breakthrough might lie in accepting that some aspects of reality will always resist language. Just as quantum particles exist in superpositions until measured, the truth about cosmic origins might hover in a kind of semantic superposition impossible to pin down with words alone. This doesn't mean we stop asking questions. It means we recognize that the answers might not sound like anything we've ever heard before. After all, if the universe could defy all expectation by springing into being, perhaps our language and our minds need to evolve just as radically to meet it. The notion of creation ex nihilo, out of nothing, echoes through sacred texts and oral traditions across millennia. In the Hebrew Bible, Elohim speaks the cosmos into being over a formless void. The Quran describes Allah as the one who originates creation, then repeats it. Even ancient Egyptian hymns tell of autumn rising from the primordial waters of none to fashion the world through divine utterance. These aren't just cultural curiosities, they're humanity's earliest thought experiments grappling with the same existential cliff that stumps physicists today. How can everything spring from absolute nothingness? What's striking isn't the diversity of these stories, but their shared thematic architecture. Whether it's the Maori sky father Rangi separated from Earth Mother Papa to create space, or the Hindu Rigveda's paradoxical hymn, wondering if even the gods know how existence began, there's a recurring recognition that origins defy ordinary logic. These traditions often employ poetic devices, metaphor, paradox, even humor, to navigate the unspeakable. The biblical "Let there be light" isn't a technical manual. It's a linguistic bridge across the unbridgeable, much like modern cosmology's quantum fluctuations or inflationary fields. Yet theology and science part ways dramatically in their handling of the unanswerable. Where religious narratives often posit a transcendent cause, a divine will or cosmic consciousness, science rigorously excludes anything beyond natural explanation. This isn't dogma but methodology. Supernatural claims can't be tested or falsified, so they lie outside science's domain. But the persistence of creation myths hints at something deeper than doctrine. They reveal a cognitive itch our species can't stop scratching. Our brains evolved to seek causes for effects, to chain events into narratives. Faced with the ultimate why, we compulsively draft scripts featuring prime movers, whether they're gods, quantum fields, or mathematical laws. The tension between these frameworks isn't just academic, it shapes how we frame the universe's birth. When Augustine wrestled with time in Confessions, arguing that God created time itself and thus there was no then, he anticipated Einstein's relativity by 15 centuries. Similarly, the Buddhist concept of dependent origination, where phenomena arise only in relation to others, finds eerie resonance in quantum physics entanglement and emergent space-time. These parallels don't validate any particular theology, but they underscore how deeply the mystery of origins is woven into human thought. Modern cosmologies, quantum vacuum, might seem light years removed from Genesis, but both attempt to solve the same riddle: how structure emerges from formlessness. The key difference lies in their tools. Where mystics invoke sacred syllables or divine breath, physicists deploy wave functions and entropy gradients. Yet both confront the limits of language when describing pre-creation states. The Tao Te Ching's "the named is the mother of all things, but the unnamed is the origin" could easily describe the quantum physicist's struggle to define the pre-Big Bang void. Perhaps the most poignant insight isn't about cosmology, but about us. The fact that hunter-gatherers huddled around fires and scientists peering through telescopes land on similar existential questions suggests something fundamental about consciousness. We're creatures haunted by our own beginnings, compelled to project narratives onto the cosmic blank. Whether those stories feature thunder gods or holographic brains, they're all testament to the same awe. that against all probability, we're here to ask the question at all. This cross-cultural obsession with origins might be the ultimate clue. When science and spirituality both strain to describe nothingness, perhaps they're not failing, but pointing toward a reality where nothing was never empty to begin with. If the universe truly sprang from random quantum fluctuations, a cosmic roll of the dice with no grand design, what does that say about the meaning of our lives? This isn't just abstract musing, it's a question that cuts to the core of human existence. On one hand, a universe born from chaos might seem to render our struggles, loves, and ambitions cosmically insignificant. After all, how much can a single life matter in a cosmos where galaxies collide and stars die without a second thought? But there's another way to see it. If there's no preordained script, no cosmic scorekeeper keeping track of our choices, then the responsibility and the power to create meaning falls entirely on us. Consider the existentialists of the 20th century, thinkers like Jean-Paul Sartre and Albert Camus, who stared into the void and found not despair but liberation. Sartre famously declared that we're condemned to be free, meaning that without divine blueprints or inherent purpose, we're forced to invent our own values through action. Camus took it further, imagining Sisyphus, the mythical figure doomed to eternally push a boulder up a hill, not as a tragic figure, but as a hero who finds joy in the struggle itself. These philosophies didn't emerge from physics labs, but they resonate eerily with a universe that might have emerged from nothingness without a guiding hand. If existence has no ultimate meaning, then every act of kindness, every stroke of creativity, every moment of connection becomes a rebellion against the void, a way of saying, even if the cosmos doesn't care, we do. Yet this freedom can feel like a double-edged sword. Without cosmic reassurance, the weight of meaning-making rests entirely on human shoulders. Some find this exhilarating, the idea that we're not pawns in some grand design, but authors of our own stories. Others grapple with what psychologist Viktor Frankl called the existential vacuum, a sense of emptiness when traditional sources of meaning, religion, cultural narratives, no longer suffice. But here's where science and philosophy converge in a surprising way. The same quantum randomness that might have birthed the universe also mirrors the unpredictability of human life. Just as particles defy deterministic paths, our choices and chance encounters shape our destinies in ways we can't fully predict. This isn't just theoretical. Studies in positive psychology show that people who actively cultivate purpose, whether through relationships, creativity, or service, report deeper fulfillment, regardless of their beliefs about the universe's origins. In other words, meaning isn't something we find out there in the cosmos. It's something we build through our actions. The astronomer Carl Sagan captured this beautifully when he said, "We are a way for the cosmos to know itself." If the universe truly arose from nothingness, then our capacity to ponder its origins, to feel awe under a starry sky or wrestle with these questions, might be the most profound twist in the story. So does a self-created universe rob life of meaning, or does it hand us the ultimate creative license? The answer might lie in how we frame the question. A universe without predetermined purpose isn't a blank void. It's a blank canvas, and that changes everything. The same quantum uncertainty that allowed existence to flicker into being also fuels the unpredictability of human potential. In a cosmos where particles can be in two places at once, where time bends, and where reality might be a holographic projection, why shouldn't our search for meaning be just as fluid, just as dynamic? The universe didn't need permission to exist, and perhaps neither do we. The James Webb Space Telescope peers deeper into cosmic history than any instrument before it, capturing starlight that has traveled nearly the entire age of the universe. Already, its infrared eyes have spotted galaxies that shouldn't exist. Colossal structures formed shockingly early after the Big Bang, challenging our models of cosmic evolution. But JWST's greatest contribution might be yet to come. By analyzing the faint chemical fingerprints of these primordial galaxies, scientists hope to reconstruct the conditions of the early universe with unprecedented precision. Did matter clump together as predicted by quantum fluctuations, or will we find anomalies pointing to something stranger, perhaps relics of a pre-Big Bang phase, or evidence of cyclic cosmology's endless rebounds? Meanwhile, quantum physicists are staging laboratory experiments that flirt with the very edge of existence. In vacuum chambers chilled to near absolute zero, researchers manipulate quantum fields to create something from nothing on microscopic scales. When strong electromagnetic fields are applied to these artificial voids, particle-antiparticle pairs spontaneously emerge, a phenomenon called the Schwinger effect, mimicking the quantum jitters thought to have sparked our universe. Though these lab-created particles are fleeting, they offer tangible clues about how reality might bootstrap itself into being. The next generation of quantum simulators aims to recreate not just particles, but space-time itself using ultra-cold atoms trapped in laser grids to mimic the birth of cosmic structure. Yet for all these advances, fundamental limits loom. Even our most powerful telescopes can't peer beyond the cosmic microwave background, the afterglow of the Big Bang that obscures earlier epochs like a dense fog. And while quantum experiments hint at how particles might emerge from void, scaling this up to an entire universe remains speculative. Some theorists argue that certain knowledge might forever elude empirical grasp, that the pre-Big Bang state could be as unobservable as the far side of a black hole's event horizon. The philosopher Karl Popper's criterion lingers like a shadow. For a theory to be scientific, it must be falsifiable. But how do you falsify a hypothesis about what existed before space and time? This tension fuels debates about the very nature of science. Must all truths be testable, or are some questions like the origin of existence best approached through mathematics and logic? The multiverse theory, for instance, posits countless unobservable universes with different physical laws. While criticized as unscientific by some, others counter that its mathematical consistency and ability to explain fine-tuning give it weight despite its untestability. Similarly, string theory's extra dimensions and loop quantum gravity's spacetime atoms might never yield direct evidence, yet their internal coherence keeps them in play. What's clear is that the tools reshaping this frontier are as much conceptual as technological. New telescopes won't just gather more data, they'll force us to reinterpret what nothingness even means. When quantum gravity experiments attempt to measure spacetime's granularity, they're not just probing physics, they're testing whether reality's building blocks can exist independently of observation. Each breakthrough seems to deepen the mystery, revealing layers of complexity beneath what we once called empty. Perhaps the ultimate revelation won't be a definitive answer, but a realization that the question itself evolves as our understanding grows, that the void we've been trying to define was never static, but a mirror reflecting back the limits of our current imagination. The coming decades may bring us closer to understanding cosmic origins than ever before, or they may show us why some horizons always recede as we approach. Either way, the pursuit illuminates something profoundly human. Our refusal to accept mystery without a fight, and our capacity to wonder about the unknowable. After all, a universe that sprang from nothingness contains its own kind of poetry, one where the act of questioning might be as close as we get to touching the void.